I now want to revisit this set from example 2 and consider whether we can form a basis using the vectors in that set. So example 2 is the quick one in a previous video where we looked at this set and said, well, it can't be linearly independent because there's too many vectors for R3. No way to get a pivot in every column, so it's a linearly dependent set. Therefore, it's not a basis. Can't meet that first requirement. Example 4 asks, okay, so it's not linearly independent. Can we form a basis for R3 by selecting some of the vectors in this set and not keeping all of them? So I started the process here. I show the steps in the row reduction in the PDF of the notes. But so I'm going to skip a few steps, skip the row reduction here because this matrix is kind of large. I set up a matrix whose columns are the given vectors. If we do some row reduction, use the steps that I showed in the notes, then you'll arrive at this for an echelon form of that matrix. We see now that we have a pivot in columns 1, 2, and 3, and we have this non-pivot column in column 4. So this tells us if you think in terms of the definition of linear independence, where let's call these vectors v1, v2, v3, v4, then the homogeneous equation c1 times vector 1, c2 vector 2 plus c3 vector 3, c4 vector 4 equals the 0 vector. So if you think of this as being augmented with a column of zeros here, when you row reduce, you're going to have a non-pivot column here, which signals that c4 is a free variable, which tells us that in the equation, in this equation, C4 is a free variable, meaning we can come up with a solution for any value for C4. So suppose we decide to let C4 equal 1, let's say. So then you'll have C1 times vector 1 plus C2 times vector 2, C3 times vector 3, plus 1 times vector 4 is equal to the 0 vector. Well, then you could solve that equation for vector 4. So vector 4 is equal to negative C1 vector 1. Now I'm starting to use vector symbols, I guess. Here, we would just move these three guys to the other side. So minus C1 vector 1, minus C2 vector 2, minus C3 vector 3. And what this equation right here tells me is that V4 then is in the span of V1, V2, V3. Because it's a linear combination. Because of that, that tells us that nothing is lost. And when we talk about the span of these vectors, we don't lose anything if we just delete vector 4. If we just delete vector 4, nothing is lost from the span because vector 4 was a linear combination of v1, v2, v3 anyway. So any multiple of vector 4 is going to be a multiple of some linear combination of v1, v2, v3. Therefore, in the span of v1, v2, v3. So like I said, this tells us that nothing is lost if we delete that last vector. And so now, imagine we do delete it, focus on just the first three columns. Now you've got a pivot in every column, which tells us the first three vectors are linearly independent. We have a pivot in every row, which tells us that the collection of the first three vectors will span R3. No matter what vector b1, b2, b3 we attach here, that's always going to be a consistent system. So if we take just the first three vectors here, that will form a basis for R3. So here's a similar question, part 2 of this video. Let H equal the span of these 4 vectors in R4. Find a basis for H. And another way we might refer to this set H, you'll see this in the homework, is we might call this the subspace of R4. Remember that if you're talking about a span of a collection of vectors, that's automatically a subspace of whatever vector space contains these vectors. So the subspace of R4 spanned by these vectors. That's another way to think about what we're calling H here. All right, we want to form a basis. So we need to know, we need a collection of vectors that is linearly independent and spans the span of these vectors, which seems a little odd. There is something obvious going on with these vectors that you may have already noticed. I mean, let's pretend like we don't notice. Let's pretend like there isn't anything obvious going on with these vectors, and I'll come back and be more explicit about what I mean there in a second. But let's suppose we just take the vectors, we set them up as the columns of a matrix, and we row reduce. This one reduces pretty quickly. So if we do 2 times row 1 plus row 2, put that in row 2, and negative 3 times row 1 plus row 3, put that in row 3 to zero out this guy. And then to zero out that 1 on the bottom, we could do negative 1 times row 1 plus row 4. Put that in row 4. And let's see what we get. So I'm leaving row 1 alone. 2 times row 1 plus row 2. So 2 plus negative 2. Negative 4 plus 4. 2 times this. Negative 2 plus 2. Isn't that nice? And then 2 times this. So 6 plus 0. And then here, negative 3 row 1 plus row 3. So negative 3 plus 3. Positive 6 plus negative 6. Negative 3 times this would be positive 3 plus negative 3. And then negative 3 times this would be negative 9 plus 0. Right. And then negative 1 plus 1. Positive 2 plus negative 2, positive 1 plus negative 1, and negative 3 plus 6. Okay, now I'm going to gloss over a couple of steps here. If we did, say, 1/6 times row 2, make that the new row 2, then that would turn this into a 1. And then we could do, say, 9 times row 2 plus row 3. That's going to make this a 0. Negative 3 times row 2 plus row 4. That's going to make this a 0. So like I said, I'm glossing over some work. I don't want to write this whole matrix 2 more times, but we'll eventually get to this echelon form. Let's go with this. And then these are all zeros. Okay. So now we can see that, well, the pivots are here and here. So we've got these non-pivot columns in column 2 and column 3, which tells us that in the equation C1 times first column plus C2 times second column plus C3 times third column plus C4 times fourth column. Let's say we're solving the homogeneous system where this is equal to 0. C2 and C3 are going to be free variables, which means we can find a solution no matter what values we want to use for C2 and C3. So suppose I choose to let C2 equal 1 and C3 equal 0, and I want to write the solution set in that case. So I'd have C1 times vector 1 plus 1 times vector 2, plus 0 times vector 3, plus C4 times vector 4 equals 0. So V2 is equal to negative C1 vector 1 minus C4 vector 4. And so what's important there then is that V2 is in the span of vector 1 and vector 4. And we could do the exact same thing if we chose instead to make C2 0 and make C3 1. We get the same result. Vector 3 is this combination of V1 and V4. So this is also true for vector 3. Both of these non-pivot columns are, that tells us that these corresponding vectors are in the span of the vectors that correspond to our pivot columns. So it's in the span of, in this case, V1 and V4. So that tells us that nothing is lost. When we talk about the span of V1, V2, V3, V4, when we talk about the span of these vectors, that's the set H, we don't lose anything if we delete vector 3 and vector 4. If we delete these non-pivot columns, nothing is lost from the span, because anything that was any multiple of V3 can be written as a linear combination of V1 and V4. And same thing with any multiple of V2. Can be written with this equation as a linear combination of V1 and V4. So that tells us then that vector 1 and vector 4 will span all of H, and they're linearly independent because you have a pivot in every column. So our basis for H will be the vector is just the first vector in this set. Oops, that's a positive 3. And the fourth vector. And the overall process for finding a basis for a vector space spanned by a collection of vectors, you set up the matrix and row reduce, and you keep the vectors corresponding to the pivot columns. You throw out the vectors corresponding to any free variables. And that'll give you your linearly independent set that spans the original set. One last thing about this example, so just to acknowledge what you may have noticed from the beginning, vector 2 here is just -2 times vector 1. And vector 3 is just -1 times vector 3. So you may have seen at the outset, oh, well, the vector 2 and vector 3, those are just multiples of V1. I don't really need those. Because when we talk about the span, we're talking about all linear combinations, so all sums of all multiples. So if the span already, as soon as you write down this vector, you've got all multiples of this vector. Then you've already got -2, 4, -6, -2 in the set. And you've already got this in the set. So you don't need to write those vectors. Those are redundancies that we want to remove when we talk about a basis.